Good evening, ma'am.
So today we'll discuss the application of differential equation, in which we are going to study two models related to motion of the study of vibration of spring when it is in motion. So let's start. Please take a note of that because I do not have the material to upload over there. So we have suppose a coil spring is attached to a surface and then with its natural length L. Okay, so its natural length is L. So when a mass M is suspending on the lower end of this coil spring, so obviously it will move downwards, then upwards, then downwards and upwards, right? Once it get the equilibrium position, then only it will be stable. So suppose you are attaching one mass to the lower end of this. So it's after getting an equilibrium position, this position is O, right? And the stretched length is now E. And up to here it was the natural length. So L plus E. So this is your equilibrium position. Now see, before going to the equilibrium position, like this is the stable position. Now it is not moving, not downwards, not upwards. But before getting or attaining this equilibrium position, let us say that, not let us say, there should be a position P somewhere here. Now this P position is varying. Means if I'll tell you roughly, suppose when we have suspended one mass to its lower end, suppose here, and this is the equilibrium position. So to get this equilibrium position, it should have gone this like this. Then this position it will get, right? So upward direction, downwards, upward direction, and then it will be stable after some time. So this P position is varying. So if I'll take it below to this, so let's say that this length is varying, a variable x. So if I'll take this length upward to the equilibrium position, it will be negative. It will be negative because we are measuring from the equilibrium position. And if it is downwards, the P position of this mass, if it is downwards, so it will be positive, right? So this is the varying position of this, and this is the equilibrium, and this is the natural length. So everything we are gonna write. Let the coil spring has natural length L so the mass M is attached to its lower end. So thereby, and let's say, and this spring comes to rest in its equilibrium position position at point O. Okay, so thereby stretching the spring by an amount T, so that the stretched length is E. Right now, in the equilibrium position, there will be two forces which are acting on the equilibrium position. There are two forces. So I'm writing here in the position of equilibrium, O, the mass M is acted upon by two forces. So one force, due to its mass M, the weight mg, right, it will act in downward direction. So first one, the weight mg. So I'm writing here acting vertically downwards. So this is arrow, means you can write acting vertically downwards. Now second one is, see, this is the motion of the spring, so obviously it will be means the Hooke's law, and Hooke's law means the force will be proportional to this, like this weight, what I'm saying, the spring force Ke acting vertically upwards. So spring force, this is second one, Ke acting vertically upwards, so in this direction. Now, because this is the equilibrium position, it is now in the stable form. Two forces are acting, one is downwards, one is upwards, and this is equilibrium position. That means these two forces are equal, then only it is an equilibrium position, right? So this is K is the spring constant by Hooke's law. You can say that it is always spring force is proportional to the stretched length, and then this is the spring constant. Okay, so thus we have at O, you can say that at O we have mg is equals to Ke. Right now, this was about the equilibrium position. Now we will study about this P position, which is varying. This is fixed one and this is varying. Before coming to the equilibrium position, let's see where is P. P can be in upward direction, in downward direction, so that we'll consider. Okay, so let P be the position of the mass M at any time t. Let P be the position of the mass M at any time t, such that OP is equals to X, right? So then X is positive, 0, or negative, according to its situation or position. According to whether the mass m is below, so below, that means positive, at means at 0, at O point, sorry, at O, or above its equilibrium position. Okay, so now we'll see the forces which are acting on this. So at P, the following forces is acting upon at P, the following forces is acted upon that. First one, see, even at this position P, first force due to its weight, due to its mass, F1 is equals to mg, right? Now it will work vertically downwards, weight always, okay? Second force, the restoring force. So restoring force means which acts to bring a body to its equilibrium position. Okay. So when the mass at peak position F2 is acting in the upward direction. Okay. So it is negative. And so it is negative. So this restoring force is always proportional to the stressed length, the complete stressed length. That means stressed length. So first stressed length was E, right? Then at P position it was X. Now because we are saying it is restoring force, means which acts to bring a body to its equilibrium position. So that X, like the position of P will depend on this. It can be positive, it can be negative, but here we'll take positive, and it is always, we are talking about this force, and it always acting in upward direction. So at position P, that means if I'll take F2 is always proportional to this X plus E. So because this is due to the length of the spring, that means again the spring constant, where K is the spring constant, you can write. So even you can write minus Kx minus Ke from the previous one, minus Kx minus mg. So this is your F2. Now next force will be the resisting force. Resisting force always acts opposite to the motion of the spring. Okay, like you can say that for example the friction. Okay, so third one is resisting force. Let's say F3 of the medium. Okay, now this is resisting force is called as the damping force. Now it is always for the small velocities. like because the spring is moving and moving upward and lower direction than before coming to the equilibrium position, you can see that the distance is going to be very less, and if distance is less means the velocity will be less. For small velocities, F3 is approximately proportional to the magnitude of the velocity. So when the mass is moving downwards, F3 acts in the upward direction. Okay, so it is also negative. F3 acts in the upward direction. So what it was saying, F3 is approximately proportional. So proportional to the magnitude of the velocity. Now dx by dt, because x was the distance, the length of that, even it will be the distance, you can say that when up. Okay, so this is the velocity. Now it is negative because it acts upward direction, opposite to the moment of mass, and now it is proportional. So that means it is equal to a dx by dt, where a is the damping constant. Now last force. Suppose you have any external force which is affecting the movement of mass or the motion of the mass or the spring. So external impressed force, that can be anything. Ft, acting in downward direction. Right, so we have four forces due to its weight, then restoring force, then resisting force, now external impressed force. Now from the Newton's law, F is equals to ma square. So a is not here damping constant, it is acceleration. That means you can write m d2x over dt square. Right, now F, the total force, that means F1 plus F2 plus F3 plus last one F4. So F1 was, if you remember, mg, then the restoring force F2, that was equals to minus kx minus mg, then resisting force, that was equals to a dx by dt, and F4 Ft, some function of p, some force. Right, now mg minus mg cancelled, so because this is second order, so take it this side, then minus a dx by dt minus kx. No, this, so it should be plus, is equals to ft. See, this is second order linear differential equation, where x is the dependent variable and t is the independent variable. M, the mass of this mass that is attached to the spring, is the damping constant, k is the spring constant, and ft is the external force. Right, so this is your general differential equation of this type of motion. Suppose if a is 0, you can take the sub cases. Case 1, if a is 0 means the motion is called undamped motion. Means there is no resisting force. Otherwise, it is called damped. So A0 means you have the differential equation m d2x over dt square plus kx is equals to ft, right? So this is your differential equation. Because A is 0, so this term will be 0. Now case 2, if there is no external force, that means ft is 0, right? And that is for all t. In this case, the motion is called free. And the corresponding differential equation will be m d2x over dt square plus a dx over dt plus kx is equals to 0, right? Now, if I simply say that free undamped motion, free undamped motion. So for free means no external force, undamped means a is equals to 0. So simply you can see that m d2x over dt square, a term is 0, kx is equals to 0. You can simply solve. Homogeneous second order differential equation. This is also homogeneous. This is non-homogeneous. So this was the model related to the motion of the spring. Next we have LRC circuit. Okay, so that is a small one. Any doubt in this?
No, ma'am.
So
No, ma'am.
okay, if you have any doubts in basics like what is resisting, restoring, so you can search and you can make it clear, because I have not a physics background. So LRC circuit, first we'll draw the circuit, the general circuit will draw, then we'll decide it, so we'll see its sub cases, right? So first inductor, then resistor, then capacitor, and then electromotive force. So according to the given values or given this, you can modelize any problem related to this, right? So we'll consider the general case, general model, then there will be the sub cases. So this is LRC circuit. CUIT. Okay, so what we'll do here, we'll just see the voltage drop across resistor, across inductor, across capacitor. Okay, so voltage drops. Now first, see, if you, even I don't remember that much physics. So, but if you remember, recall the concept. First, voltage drop across resistor is always equal to, so let us denote the voltage drop ER. This across resistor is always equals to, means it is always proportional to the current. So we'll just take the Ri, right? That means, yeah. Okay, so it is, I'm writing here across resistor, then voltage drop across the inductor, EL is always equals to proportional to di by dt. So this is the inductance constant di by dt. So this is across inductor. Now again across capacitor, EC, now you know that by Kirchhoff's voltage law, the sum of the voltage drop across resistor, inductors and capacitors is equal to the total electromotive force in a closed circuit. So when we are talking closed circuit, then only it will be equal to all of these voltage drops across the resistor, inductor and capacitor. Okay, so simply I'm writing by Kirchhoff's laws, voltage law even, the sum of the voltage drop across resistor, inductor and capacitors is equal to the total electromotive force in a closed circuit. Okay, so because already we have denoted E as an electromotive force, you can denote here electromotive force. So we'll just write E is equals to ER plus EL plus EC. So E is equals to EL plus ER plus EC in a closed circuit, right? So E, the electromotive force, value of EL, L di by dt, R, Ri, this was EC, that means Q by C. So this is your E, right? So we'll just write in a proper form, L di by dt, right, plus Ri plus Q by C is equals to E, where Q is the charge. Okay, so you know that current is always equals to dq by dt, right? So if I simply take here I value, if I simply put I value here, I value means then it will be the double derivative of dq by dt, right? So L d2q by dt square. Now value of I dq by dt plus q by C is equals to E. So this is your second order differential equation. Second order differential equation in the single dependent variable Q. Q means charge here. Okay. Now this is your first equation. Now if we want a differential equation in terms of current, so what we do here, we simply take this as A equation, differentiating A with respect to T. So you will get L d2I by dt square, right, plus R di by dt and plus 1 by C. Now Q charge depend on T. That means it is not constant. Constants are L, R and C. These are the proportional constants. Okay. So dq by dt is equals to de by dt, electromotive force. Always depend on time, right? Now dq over dt is again I. So when you need to find the this current, use this differential equation. Now see, now it will use the sub cases you can conclude. Like if the circuit contains no capacitor, so no capacitor means the related term will be 0 here. Here related term will be 0. Okay. If no inductor, that means this term will be 0, this term will be 0, this term will be 0. Right? So sub cases you can decide. But when we are writing the model, suppose in exams it been asked like find the charge, then use this differential equation and you will have the values of L, R and C. And even if there is mentioned that there is no capacitor in that circuit, so just simply take it as 0. Okay, and electromotive force will be given to you and simply write and solve this differential equation, you will get the solution of Q. And if you need to find the current, then use this differential equation. See, the change is here it is simple E, here it is dE by dt. The whole equation is same in terms of this Q, I, right? And even the coefficients are same. The change is here it is simply E and here it is the derivative of E. Okay, so the sub cases you can conclude. So this was your last topic of the 4th module. Your syllabus is first this 3rd and 4th module only for CAT 2 exam. Any doubt?
No, ma'am.
Okay then. But I'll take the classes because this time they are giving very less syllabus compared to the previous CAT 2 exams. So if I'll just skip the class, then I won't be able to finish the syllabus for final exams. So still we have 2 more classes in this week. So I'll take both the classes. I'll start 5th module.
Excuse me, ma'am.
Ma'am, kindly upload the material, ma'am.
Okay, I'll upload.
Excuse me, ma'am.
Yes.
Ma'am, what is the CAT 2 syllabus?
CAT 2 syllabus is module 3rd and 4th.
Okay, thank you, ma'am.
And because third means the differential equation, 4th is again differential equation, right? But different methods. Like in 3rd, we have method of operation of parameter, undetermined coefficient, Cauchy-Euler equation, but still they are differential equation, right? So the pattern is not divided like from this module, this marks and this module, this marks. Differential equations, you will get 3 questions only.
Okay, ma'am.
Okay, so now I'll take attendance.
Ma'am, paper pattern?
That's what I'm saying. Paper pattern means both the modules related to differential equation, right? So only 3 questions you will get.
Okay.
3 questions related to differential equation. That's it. I'm taking attendance. Please mark your attendance, everybody. who have marked their attendance may leave.